Welcome to this explainer. Today, we're going to look at database design through an entirely different lens. We aren't just going to treat these concepts as dry, abstract theory. Instead, we're looking at them for what they truly are, the foundational engineering blueprints required to organize our entire digital world. I want you to think of conceptual modeling as the absolute essential architectural groundwork. You know, the stuff that simply has to be laid down before a single brick is placed or a single line of code is written. Okay, let's dive right in.
So think about this. How do you actually turn real-world chaos into perfect digital order? It's a pretty high-stakes question, right? Our source material points out a really vital learning outcome here. Before we jump into the fun stuff, the technical implementation, we absolutely have to apply a structured approach to conceptual modeling. Because let's face it, the real world is messy. It's filled with countless interacting elements. And to capture all of that in a database, we need a flawless blueprint. We need the entity relationship model.
Here's our roadmap for getting there. First, the blueprint of databases. Second, core ER building blocks. Third, enforcing rules and constraints. Fourth, the extended ER model. And finally, number 5, real-world system design.
Let's kick things off with Section 1, the blueprint of databases.
We literally start at step 0. According to the core learning objectives we're looking at, the absolute first step in database design is to evaluate your problem statement and identify crystal clear objectives. You simply cannot design a system if you don't know the exact scope of the real-world problem you're trying to solve. Getting that precise problem statement nailed down is crucial so you know exactly what entities and relationships actually need to go into the design. It's really all about applying a strict, structured engineering approach right out of the gate.
Moving right along to Section 2, core ER building blocks.
All right, let's talk about our foundational brick, the entity type. An entity type represents a distinct real-world object or concept within your database. The source material uses a hospital management system as a case study, which is honestly a fantastic way to look at this. In that hospital setting, an entity type would be something like a patient or a doctor. They're completely distinct, definable concepts that we know we need to store data about.
Next up, we have attributes. Now, if entity types are the bricks themselves, attributes are the specific characteristics of those bricks. They're the specific properties or details that actually describe the entity. So for our patient entity, the attributes would be things like their name, their date of birth, or their medical history. For a doctor, it might be their specific medical specialty. Basically, attributes are what give our raw entities actual meaning and context.
But here's the catch. How do we actually tell all these entities apart? That is where keys come in. Keys are unique identifiers that distinguish one entity instance from another within an entity set. Imagine running a hospital with hundreds of patients named John Smith. Without a key, like a unique patient ID number, our nice, neat digital order completely collapses back into real-world chaos. Keys are that vital locking mechanism ensuring we can precisely locate specific data without any confusion.
Now, while engineering our database, we're going to encounter something called weak entity types. These are entities that honestly just cannot exist on their own. They rely entirely on a strong entity. Think of a patient's emergency contact in our hospital example. That contact record has literally zero reason to exist in the database if the patient themselves is removed. It's a dependent structure, fundamentally reliant on the primary entity.
Okay, so we've got our raw materials, right? Our entities, attributes, and keys. Relationship sets are essentially the mortar that connects all these blocks together. They link entity types, categorize their interactions, and allow us to apply true engineering fundamentals. For example, a relationship set defines how the doctor entity interacts with the patient entity. Maybe we call it a treats relationship. This is what ensures a highly structured representation of the incredibly complex realities happening inside our hospital.
Which brings us to Section 3, enforcing rules and constraints.
Now that we have our building blocks in our mortar, we need to lay down the absolute laws of physics for our structure. Our source text heavily emphasizes identifying relevant processes and parameters to implement constraints effectively. This is where mapping cardinalities come in. They dictate the numerical limits of relationships. Is it a one-to-one relationship, or maybe one-to-many? For instance, one doctor might treat many patients, but a specific patient room might only be assigned to one patient at a time. By identifying these processes and applying mapping cardinalities, we're enforcing strict database constraints. This isn't just administrative paperwork, this is literally how we ensure absolute data integrity and consistency across the entire system.
Jumping into Section 4, the extended ER models.
Here is where we step up into advanced computer science engineering theory.
We're moving out of the basics and into the expansion phase, upgrading our standard building into a complex, highly specialized facility. When we compare the standard ER model, which just has entities, attributes, and keys, against the Enhanced Entity Relationship Diagram, or EER model, things get interesting. The EER model incorporates generalization, specialization, aggregation, and inheritance. Because when you're tasked with documenting system requirements from stakeholders for really complex real-world problems, the standard ER model sometimes just isn't enough to capture those advanced nuances.
Let's actually break down these advanced ER concepts for a second. Specialization and generalization allow us to create hierarchies. Back in our hospital, we might have a generalized entity simply called employee, but stakeholders will quickly tell you that doctors, nurses, and janitors all have very different attributes. So we use specialization to branch employee out into subentities. Those subentities then use inheritance to keep the common attributes like an employee ID, while adding totally specific ones like a medical license number. Aggregation, on the other hand, allows us to treat a relationship between entities as a single entity itself. Applying these principles lets us solve some seriously complex engineering puzzles.
And finally, Section 5, Real-World System Design.
This design workflow perfectly summarizes the engineering approach we've been talking about. Step 1, evaluate your problem statement and define the scope. Step 2, identify and document those system requirements by actually sitting down and listening to the stakeholders. Step 3, apply absolutely everything we've learned to develop comprehensive ER and ER conceptual models. This is the action-oriented workflow required to take a messy, chaotic, real-world problem and translate it into a pristine database design.
And here we have the ultimate application, designing the hospital management system itself. We take our problem statement, we apply our engineering fundamentals, we define our strong entities like doctors and wards, we establish our weak entities, we lock it all down with unique keys and mapping cardinalities to ensure data consistency. And finally, we use advanced ER concepts like generalization to map out the entire complex hierarchy of hospital staff. It represents the complete journey from raw, unfiltered stakeholder requirements all the way to a fully structured, conceptual database model.
So, I'll leave you with this to think about. If a database model is only as good as the requirements it captures, what critical reality might be missing from your blueprint? Because a perfectly drawn diagram is completely useless if it doesn't solve the actual problem. Successful conceptual design relies entirely on accurately evaluating the ever-changing reality of stakeholder needs and using these structured tools to represent that reality flawlessly. Thanks for joining me for this explainer, and keep building those perfect blueprints.